Alright, so this week we are connecting the ideas of potential energy stored within springs, elastic potential energy, to our ideas of mechanical energy that we were working with a lot right before our schools closed down about a month and a half ago, which is crazy to think about. So in this simulation, we're going to come over to this lab part of the simulation. I'm going to click there. What you all are going to be using is the default settings here, so a mass of 100 grams is right for your work. This 3-notch spring is right for your work as well, and I include the spring constant right within the work. I think it's a little over 6.1 newtons per meter, so that's what you're going to use. For this demonstration, just for what I'm going to do in this video, I'm going to set that mass to 150 grams, and I'm going to set the spring constant to the 5th notch, which is, I believe, 7.84 newtons per meter. But those default settings are right for you. Now, a couple things that you do need to click as soon as you come into the simulation. You want to set this damping to none. I'll talk about that probably later in the week, why that's important, and if you want, you can sort of investigate what damping is. But for now, I'm just going to set that to none. I'm going to stay on Earth, and I'm going to go ahead and click actually all of these different boxes up here: our displacement, our mass equilibrium, movable line, and period trace. And big picture, before I start doing any calculations or anything like that, what we're doing this week is we're looking at sort of 3 different points within the same system. So if I just sort of let this go, if I let that spring bounce, there's sort of a bottom, middle, and top part of that simulation. And if I draw this very unimpressively on the right side, we are looking at those sort of 3 different key points. And so in the bottom, that bottom point, that like lowest part of this trajectory, where if I let it bounce sort of at the bottom of this period trace that we can see, that's where we're going to focus our work on today, is on that bottom part. On Tuesday's work, so on tomorrow's work, we are going to look at sort of a highest point. So at the very top of that period trace, we're going to look at that tomorrow. And then on Wednesday's work, since this is the toughest one to analyze, we're going to look at that sort of intermediate middle point of this simulation. And at each 3 of those different points, we could calculate 3 different individual types of energy. And we've done this partially before with our roller coasters. We could calculate a gravitational potential energy, we could calculate a kinetic energy, and we could calculate now an elastic potential energy. And we could do that again at all 3 of those points. So I could write again, and I'm not going to do this for all 3 because I think you get the point. We could calculate a potential, a gravitational potential, kinetic, and elastic potential energy. But I'm going to erase that blue stuff because we are only focusing on that bottom point within the system that I drew in pink for now. As a quick reminder of how we calculate those different things, I'm going to write this in black. Our gravitational potential energy, we can calculate with mgh, where as long as we're on Earth, which we are for now in this simulation, this g is 9.8 meters per second squared. Height, be careful when you measure height. In a second, I'm going to go over how to do that. But it's not the same as displacement, which we've been measuring with the ruler in the simulation before. So height, I'm going to talk about more when we get there. Our kinetic energy is 1/2 mv squared. M in both of these equations is, of course, mass. V in this kinetic energy equation is velocity, because kinetic energy is the energy of motion, the energy of movement. And then our most familiar, or at least most recent energy that we've learned about, is elastic potential energy, which is 1/2 kx squared. And the first thing that I ask you to do is actually to calculate this elastic potential energy. And to do that, in your case, you'll know what this spring constant is. Again, for that 3-notch spring, it's a little over 6 newtons per meter. I think it's 6.125 newtons per meter. And then the displacement, I actually tell you at first what to set that to, just so that we're all getting similar answers. And so right now I've clicked pause. I'm going to bring out this ruler, though, so that I can actually measure the displacement vector. So this green vector that's shown up on the simulation on the left, that actually gives us our displacement. So I'm going to go ahead and stretch this mass down so that it's at a displacement. And in your cases, you're going to stretch it to 50 centimeters. Only for this video, for this example, I'm going to stretch down to 60 centimeters just so that you can see another example of how to do this. So right now, I've stretched so that we've gotten a displacement of 60 centimeters. And I can actually go ahead and start calculating that elastic potential energy now. And I'll do that in pink now. So our elastic potential energy at that bottom point is 1/2, and in my calculator I'm going to plug that in as 0.5 times, and then for this 5th notch, so again, you guys are using the 3-notch spring. For my 5th notch spring though, the spring constant there is 7.84 newtons per meter, and the displacement at this bottom lowest point here is 60 centimeters, but I'm going to convert that to meters. We should always work with meters when we are plugging into any of these energy equations. We should really always be calculating with our base units of meters, seconds, kilograms, and then all the offshoots of that, like newtons and joules and things. So our 60 centimeters is the same thing as 0.6 meters. So all I did really was I moved the decimal twice to the left to get this into meters. And so that's what I'm going to end up plugging in to our equation. And when I'm plugging this into my phone calculator, the way that I tend to do this is I plug in 0.5 for that half, and then I multiply by 7.84. 0.5 times 7.84 times 0.6 times 0.6. And what I got for that, and I'll write that at the bottom here, is 1.41 joules. And I rounded that a little bit. What the full answer was 1.4112, but I'm just rounding that to 1.41 joules. And so again, I took the spring constant that I just knew from like last week's work. For yours, I wrote it directly in the problem because you guys have already spent enough time like determining those spring constants, just over 6 for you all. I used 7.84 for the 5-notch spring, and then this 0.6 meter displacement was the same as 60 centimeters, which was just what I decided to sort of pull this mass down to. For you all at first, I asked you to pull it down to 50 centimeters, or you'll be able to figure out what that would be in meters. So the next thing that I ask you to do, the next step here, is to calculate another one of these 3 types of energies. So we'll go to gravitational potential energy next. So our GPE is m times g times h. Now, the real thing to be careful of here is measuring this height. So we know what the mass is. In your case, it'll be 100 grams. For me, it's going to be 150 grams. We're on Earth, so g is still 9.8 meters per second squared, and it says that over here in the simulation as well. But for this height, I'm going to have to use this meter stick again, and I'm actually going to help myself out by putting this little movable line right in the middle, or right through the center of that mass. And the reason for that is that when we measure this height, we want to measure measure up from this blue line here up to the middle of the mass. So we're not measuring to the bottom, not measuring to the top, we're going right to the center of mass. So I'm going to move this up a little bit so that the very bottom of that meter stick is right on this sort of ground, or our height equals 0 line. And to determine what this height is, we actually need to do a little bit of math because we're measuring from 100 centimeter mark. So I'm going to write height is equal to 100, because that's where we start, minus about 72 centimeters. So it looks like the height is 28 centimeters, which is the same as, and then again, just like how we converted our 60 centimeters to 0.6 meters, I'm going to move the decimal twice to the left to get 0.28 meters. And so that's actually the height that I'm going to plug into our gravitational potential energy equation. Was I measured from this bottom blue line, so at 100 centimeters, just because of how the simulation automatically orients the meter stick, up to wherever this center of mass was. And so I had to just subtract those numbers to find what that actual distance upwards that height was, and then I just had to convert that to meters. And so once we have that, calculating gravitational potential energy is not going to be a problem for you. We take our mass. The only thing that could maybe also trip you up here is converting our mass into kilograms. Again, we always want to work with base units. So right now I have 150 gram mass. I know that that's the same as 0.15 kilograms, though. So this 0.15 you could also write as 0.150 or 0.150 kilograms. All I did was I moved the decimal for my mass to the left 3 times, so 150 becomes 0.150. Then our G is 9.8, and our height is this 0.28 meters that we found by measuring it from the ground up to the center of mass. And at this point, it's just a plug-in, so 0.15 times 9.8 times 0.28 is 0.4116. I'm just going to record 0.41 joules here. Okay, so we've gotten our elastic potential, we've gotten our gravitational potential. The one left that we have to calculate is kinetic energy. So I'm going to go ahead and erase some of this work up here. I'm going to leave the overall drawing, leave the results that we've gotten so far, but I'm going to erase all of this stuff for now. And what we're going to be asked to do next is to calculate that one missing energy. So we just haven't calculated kinetic energy. And in order to do that, there are a couple different ways to think about it. One is if you were in lab, so we would have done this in class, if you had just pulled that mass down and you hadn't let it go yet, this mass isn't moving yet. And we know that kinetic energy is the energy of movement, but if we're not moving, we shouldn't actually have any kinetic energy. Another way to confirm that in the simulation, if you look over to the left side of that simulation, we've got this energy graph, and I can see in the light blue, that's elastic potential. We have a good amount of elastic potential. Then down here in the darker blue, we have some gravitational potential. And then we actually have, at this point, no kinetic energy. There's no little green bar up here. And so I know, just either from intuition or from the simulation, that we actually have 0 joules of kinetic energy. So this mass isn't even moving yet. Now, the absolute last thing that I ask you all to do is to calculate mechanical energy. And in the past, when we were working with our roller coasters, we talked about mechanical energy being the sum of gravitational potential plus kinetic energy. And then we looked at systems where this was conserved sometimes when we assumed that. You all designed experiments to test whether or not that was a valid assumption. But our one addition to this equation is that now, since we have a system with a spring in it, we're going to include elastic potential energy within this equation. And so to calculate that mechanical energy for this sort of bottom point in this oscillation, or maybe when it's returned down to that point in the oscillation, we're just going to add up those 3 different types of energy. So our gravitational potential energy was 0.41 plus 0 joules of kinetic energy plus 1.41 joules of elastic potential energy. And if you plug that in, I think that should be 1.882 joules of mechanical energy present in this system. And that would be our answer. And then for the rest of this sort of beginning part of the week, you're going to be testing and seeing if this energy is conserved or not, or how does maybe that change? How do these individual energies that make this up fluctuate also as you go through this system? Big key points to remember. Remember the difference between how we measured this displacement as the green vector and how we measured this height, where we have to move the meter stick and we have to measure from this bottom blue line up to that center of mass in there. So keep that in mind as you go through this week's work.